Hello, and welcome to Space for Sleep. The Milky Way is the one galaxy we can never see from the outside. That is the first strange fact about home. We can photograph Andromeda. We can measure the spiral arms of distant galaxies. We can see barred spirals, elliptical galaxies, dwarf galaxies, colliding galaxies, and galaxies so far away that their light began traveling before Earth existed. But the galaxy that contains us is different. We live inside it. We are embedded in its dust, surrounded by its stars, moving with its disk, and carried around its center at hundreds of kilometers per second. We cannot step outside the Milky Way and look back. So everything we know about it has been reconstructed from within, from star counts, radio maps, infrared surveys, parallax measurements, stellar chemistry, the motions of gas clouds, the orbits of ancient clusters, the wobble of satellite galaxies, and the invisible gravitational field of dark matter. The Milky Way is not a picture we were given. It is a structure we had to infer. And the structure that emerges is far more dramatic than the pale band in the night sky suggests. The Milky Way is a barred spiral galaxy, roughly 100,000 light-years across in its bright stellar disk, surrounded by a much larger halo of old stars, satellite galaxies, hot gas, and dark matter. It contains hundreds of billions of stars, probably hundreds of billions of planets, giant molecular clouds where new stars are forming, ancient globular clusters older than the Sun by billions of years, streams of stars torn from swallowed dwarf galaxies, and at its center a supermassive black hole called Sagittarius A star, with the mass of about 4 million suns. This is where every human story has happened. This is where Earth formed, where the Sun was born, where every atom in your body was assembled from earlier generations of stars, and where our planet is still moving now, not stationary in space, not separate from the galaxy, but orbiting inside it as part of one immense rotating system. The Milky Way is not just a background. It is the physical environment that made us possible. To understand the Milky Way is to understand the larger home inside which Earth has always existed. The Milky Way was not always understood for what it is. For most of human history, the band of light visible on a clear night was simply a feature of the sky, beautiful, sometimes associated with myth or the divine, but not understood in any structural sense. Aristotle believed it was an atmospheric phenomenon, produced by the burning of stellar exhalations in Earth's upper atmosphere. It was Galileo, turning his telescope to the sky in 1610, who first resolved the Milky Band into individual stars, revealing that what appeared to the naked eye as a continuous, diffuse glow was actually composed of countless individual stars, too densely packed to be separated by the naked eye, blending together into the glow we observe. This was a profound realization. The Milky Way was not a cloud or an atmospheric effect, but a vast system of stars, far more stars than anyone had previously imagined the sky to contain. But understanding the Milky Way structure, its shape, its size, our position within it, required a much longer, more difficult process of investigation. In the 18th century, William Herschel, the same musician turned astronomer who discovered Uranus in 1781, made the first systematic attempt to map the Milky Way by counting stars in different directions across the sky. His approach was ingenious in principle. If you could count stars in every direction and assume that all stars have roughly the same intrinsic brightness, then a direction with more stars visible to a given depth is one where you're looking through more of the stellar system, and a direction with fewer stars is one where the system is thinner or where you're approaching an edge. By counting stars in 683 regions of the sky and combining the counts, Herschel produced the first map of the Milky Way's shape, a somewhat flattened, irregular disk, with our solar system positioned roughly in the middle. Herschel's map was wrong in several important ways, but wrong in an instructive fashion. The most significant error was the assumption that all stars have similar intrinsic brightness, an assumption we now know to be dramatically false. Stars vary enormously in their true luminosity, from dim red dwarfs far less luminous than our Sun to blazing supergiants thousands of times more luminous. This variation means that a direction that appears star-poor might simply be a direction where most stars are intrinsically dim, not one where the galaxy is thinner. More importantly, Herschel had no way of knowing that the galaxy is permeated by clouds of interstellar dust and gas that absorb and scatter starlight, making stars appear dimmer than they really are and hiding entire regions of the galaxy from view. In the direction of the galactic center, the Milky Way's densest, most star-rich region, toward the constellation Sagittarius, the view is almost entirely blocked by intervening dust, and a simple star count in that direction tells you almost nothing about the true stellar density there. The realization that dust was obscuring much of the Milky Way, and that this obscuration was causing serious errors in estimates of the galaxy's structure and our position within it, came gradually through the late 19th and early 20th centuries. The American astronomer Robert Trumpler, in 1930, provided definitive evidence for interstellar extinction by studying clusters of stars at known distances and finding that their apparent faintness was consistently greater than their distances alone could explain. The extra dimming was from dust along the line of sight, reducing the brightness of distant objects and distorting any distance estimate that didn't account for it. The correct understanding of our galaxy's large-scale structure required finding objects bright enough, or detectable at wavelengths not blocked by dust, to serve as tracers of that structure across the tens of thousands of light years separating different parts of the galaxy. A key step came from studies of globular clusters, dense, spherical clusters of tens of thousands to millions of older stars, conducted by the American astronomer Harlow Shapley in the 1910s and early 1920s. Shapley measured the distances to numerous globular clusters scattered across the sky using variable stars within them, stars that pulsate in brightness with a period directly related to their intrinsic luminosity, serving as reliable standard candles for measuring astronomical distances. He found that the globular clusters were not distributed symmetrically around our local position in the galaxy, as Herschel's picture had implied, but were overwhelmingly concentrated in one direction, towards Sagittarius, indicating that the center of the galaxy lay in that direction, far from where we sit. Our solar system, Shapley concluded, was nowhere near the center of the Milky Way, but rather in its outer regions, far from the central concentration of mass and stars. This was a significant conceptual readjustment. Just as Copernicus had displaced Earth from the center of the solar system 4 centuries earlier, Shapley's work displaced our solar system from the center of the Milky Way, relegating us to an unremarkable position in the outer portion of a vast stellar system. Our Sun is not special in its location any more than it is special in its size or luminosity. It is an ordinary star, sitting in an ordinary part of an ordinary galaxy, remarkable only for the complex chemistry and biology that has developed on one of its planets. Mapping the Milky Way from inside, it is one of the most difficult observational problems in astronomy. The difficulty begins with perspective. Imagine trying to map a forest while standing inside it, with trunks blocking the view, fog between the trees, and no hill from which to look down. Nearby trees dominate your view. Distant ones merge into haze, and some parts of the forest are hidden completely. That is approximately the problem astronomers face with the Milky Way. Except the trees are stars, the fog is interstellar dust, and the forest is 100,000 light-years wide. Distance is the first obstacle. A star's apparent brightness tells you very little unless you know how bright the star truly is. A dim star nearby can look like a bright star far away. A luminous giant at great distance can look like an ordinary star close by. To map the galaxy, astronomers need reliable distances, and measuring distances across a galaxy is not simple. The most direct method is parallax, the tiny apparent shift in a star's position as Earth moves from one side of its orbit to the other. Nearby stars appear to shift slightly against the background of more distant stars, just as your finger seems to shift position against a wall when you look at it first with one eye and then the other. The shift is extremely small. For stars thousands of light years away, it becomes almost unimaginably tiny. But with sufficiently precise instruments, parallax gives direct geometry, not a model, not a guess, but a measurement. This is where the Gaia space mission transformed galactic astronomy. Gaia has measured the positions, motions, brightnesses, and colors of more than 1 billion stars with extraordinary precision, turning the Milky Way from a hazy structure inferred from selected tracers into a dynamic, moving, three-dimensional system. Gaia does not see every star in the galaxy. No survey can. Dust blocks some regions. Faint stars fall below the detection limit, and the far side of the disk remains difficult. But Gaia has given astronomers the most precise map ever made of the galaxy's stellar motions, and those motions reveal history. Stars do not simply mark where they are. Their velocities show where they have been. A group of stars with similar chemical composition and similar unusual orbits may be the debris of a galaxy the Milky Way swallowed billions of years ago. A ripple in the disk can record a past gravitational disturbance. A moving stream of stars in the halo can mark the path of a disrupted globular cluster or dwarf galaxy. The Milky Way is not a still object. It is an archive in motion. This is why modern maps of the Milky Way are not only maps of position. They are maps of velocity, chemistry, age, and ancestry. Every star carries a chemical fingerprint from the gas cloud that made it. The abundance of iron, oxygen, magnesium, silicon, carbon, and dozens of other elements tells astronomers what kind of stars enriched that gas before the star formed. Stars born in the same region at the same time often share similar chemical patterns, even after their orbits have carried them far apart. This field, sometimes called galactic archaeology, treats stars as fossils, not dead fossils, but living records of the galaxy's earlier states. The Milky Way, then, is not mapped only by where its stars are. It is mapped by how they move, what they are made of, and what their chemistry remembers. Let's build up a precise, detailed picture of what the Milky Way actually looks like, starting with its large-scale shape and then drilling down into its components. The Milky Way is a barred spiral galaxy, classified by astronomers using a system that describes its most prominent structural features. The spiral part refers to the spiral arms, arcing structures of relatively denser gas, dust, and star-forming regions that wind outward from the galaxy's central regions, traced by the bright, short-lived massive stars that form within them and illuminate the surrounding gas with their ultraviolet radiation. The barred part refers to an elongated bar of stars crossing the galaxy's central region, running through the nucleus and extending outward on either side before giving way to the spiral arms. Barred spirals are actually among the most common type of spiral galaxy in the nearby universe, with roughly 2/3 of observed spiral galaxies showing a bar structure, suggesting that bars are a natural and relatively long-lasting feature of spiral galaxy dynamics rather than a temporary or unusual configuration. From our embedded vantage point within the disk, we cannot directly observe the Milky Way's spiral structure in its entirety the way we can see the structure of nearby galaxies like Andromeda or the Triangulum Galaxy. Instead, we must infer it from careful mapping of specific tracers, objects, and features whose distribution in space reveals the underlying spiral pattern. Historically, radio observations of neutral hydrogen gas, which emits a characteristic radio signal at a wavelength of 21 centimeters regardless of whether any nearby stars are illuminating it, and which can be detected even through dust clouds that block visible light, were particularly important in mapping the large-scale distribution of gas in the galaxy and revealing the general outlines of its spiral structure. More recently, surveys of masers, compact, brilliant radio sources associated with regions of active star formation, and of massive young stars have refined the picture substantially. The current picture describes the Milky Way's disk as having a diameter of roughly 100,000 light-years, though the precise boundary of the disk depends somewhat on how it's defined. The density of stars and gas tapers off gradually rather than ending sharply, and there are stars, gas, and even evidence of active star formation detected at distances significantly greater than the traditional 100,000 light-year figure. Recent surveys have found stellar structures at distances of 200,000 light-years or more from the galactic center that may represent the outer, irregular fringes of the disk, or may be distinct structures associated with the galaxy's history of interactions with smaller satellite galaxies. The evidence is still being evaluated and interpreted. The scale of the Milky Way is difficult to hold in the mind because the numbers are not merely large. They belong to a different category of distance. Light crosses the distance from Earth to the Moon in a little over 1 second. It crosses the distance from the Sun to Earth in about 8 minutes. It takes more than 4 years to reach the nearest star system. But to cross the bright disk of the Milky Way from one side to the other, light needs about 100,000 years. A signal sent from one edge of the galaxy when early humans were living in Africa would only now be reaching the opposite edge. And the disk is only the bright, star-rich part. The halo of dark matter, satellite galaxies, hot gas, and ancient stellar debris extends much farther. The Milky Way is not a neat glowing wheel with a sharp border. Its visible structure fades gradually into a larger gravitational environment. Stars thin out. Gas becomes sparse. Satellite galaxies orbit in the outer darkness. Dark matter dominates the mass budget. The galaxy becomes less like a solid object and more like a gravitational ecosystem. Even our position in the disk is more dynamic than it feels. The Sun is about 26,000 light-years from the galactic center, but it is not sitting still. It orbits the center at roughly 220 kilometers per second, completing one orbit in something like 230 million years. Since Earth formed, the Sun has gone around the galaxy only about 20 times. The dinosaurs lived during a previous galactic orbit. The first animals lived several orbits ago. The Sun's path through the galaxy is not a background detail. It is part of Earth's long environmental history. The solar system also oscillates above and below the galaxy's midplane as it orbits, passing through the denser plane and then moving out again. The connection between these passages and events on Earth, such as comet showers or biological changes, is debated and not established in any simple way. But the larger point remains. Earth is not merely orbiting the Sun. The Sun and Earth together are traveling through a changing galactic environment, inside a disk of stars, gas, dust, magnetic fields, and dark matter. The disk is not flat in the way a tabletop is flat. It is warped, bent out of its average plane, particularly in the outer regions, in a shape sometimes compared to the brim of a hat turned downward on one side and upward on the other. This warp, extending across the outer tens of thousands of light-years of the disk, is thought to be caused by gravitational interactions with the Milky Way's large satellite galaxies, most likely the Large and Small Magellanic Clouds, which we will discuss later, whose gravitational influence tugs on the outer disk as they orbit through the galaxy's halo, gradually distorting it from planarity. The disk's thickness is not uniform. The central region of the disk, called the bulge or the central bar, is markedly thicker than the outer disk, containing an older, more evolved stellar population in addition to the bar-shaped structure of stars that gives the galaxy its barred spiral classification. The outer disk has a relatively thin stellar disk, only a few hundred light-years thick in terms of where most of the stars reside, plus a somewhat thicker component of older stars that extends vertically for a few thousand light-years above and below the plane. On the grandest scale, the Milky Way's disk contains roughly 90 to 100 billion stars, the bulk of the galaxy's stellar population, along with enormous amounts of gas and dust that represent the raw material for ongoing and future star formation. The spiral arms of the Milky Way are among its most distinctive and scientifically interesting features, and understanding them properly requires a conceptual shift from how they might initially appear to be structured. A spiral arm is not a fixed physical structure, not a rigid blade attached to the galaxy's core, rotating as a unit like a propeller. If it were, the differential rotation of the galaxy, the fact that regions closer to the galactic center complete their orbits faster than regions farther out, just as the inner planets of the solar system orbit the sun faster than the outer ones, would have wound the arms into tighter and tighter spirals over billions of years, until they became indistinguishable from the general disk. Astronomers call this the winding problem, and it arises if you imagine spiral arms as material structures that rotate with the galaxy. The resolution of the winding problem is that spiral arms are not primarily concentrations of specific stars or gas clouds that stay together as a unit, but rather density waves, regions of slightly enhanced density that move through the galactic disk as a wave moves through water, without the water itself traveling with the wave. Gas, dust, and stars flowing around the galactic center in their orbits pass through these density wave regions, spending some time in the arm and some time in the interarm regions, the same way traffic on a highway might bunch up near a slow truck and then spread out again once past it, with the traffic jam region remaining roughly stationary even as individual cars continuously move through it. As gas passes through the denser environment of a spiral arm, it is compressed, and this compression can trigger the collapse of giant molecular clouds, dense, cold accumulations of hydrogen molecules and dust, into clusters of new stars. The most massive stars produced in this process are extraordinarily luminous but extraordinarily short-lived, burning through their nuclear fuel in only a few million years and dying in supernova explosions long before they have time to drift significantly away from where they formed. This is why the spiral arms appear so bright. They are preferentially marked by the short-lived, brilliant blue and blue-white stars of recent star formation, and by the glowing clouds of ionized hydrogen gas illuminated by those stars' ultraviolet radiation, even though the arms contain only a modest enhancement in the total density of all stars compared to the interarm regions. Our solar system sits in the outer portions of the Milky Way, between two of the galaxy's main spiral arms, in a smaller feature sometimes called the Orion arm or local arm, an apparent spur or minor arm lying between the larger Sagittarius arm inward of us and the Perseus arm outward of us. The precise mapping of the nearby spiral structure, and particularly the characterization of the local arm as a genuine, if shorter, arm segment rather than merely a connecting spur, has been one of the ongoing objectives of precision radio astrometry surveys, which use the apparent positional shift of maser sources against background objects as the Earth moves in its orbit around the Sun. The same geometric parallax technique used for much closer stars to measure distances with extraordinary precision. The identification of the Milky Way's global spiral structure, including the number of major arms and the precise geometry of the bar, has undergone substantial revision over the past several decades as observational data has improved. Early radio surveys suggested a four-armed spiral pattern, with four major arms extending from the ends of the central bar through the disk. More recent infrared surveys using the Spitzer Space Telescope, which can observe stellar populations throughout the disk without the severe dust obscuration that affects visible light observations, have suggested that the Milky Way may be better described as a two-armed spiral at its largest scales, with the other apparent arm-like features being shorter spurs and segments associated with particularly intense star-forming regions rather than true, full-length spiral arms. The current consensus picture, still somewhat uncertain and actively studied, favors a galaxy with two dominant spiral arms, the Scutum Centaurus arm and the Perseus arm, extending from opposite ends of the central bar, with additional arm segments and spurs including the Sagittarius arm and our own local arm. The spiral arms are therefore not only shapes, they are processes. Inside them, cold molecular gas is compressed, massive stars are born, ultraviolet radiation carves cavities into surrounding clouds, stellar winds push material outward, and supernovae eventually return enriched gas to the interstellar medium. A spiral arm is a place where the galaxy briefly concentrates its raw material and converts some of it into stars. But the arms are not safe or gentle regions. They contain some of the most energetic young stars in the galaxy. Massive O-type stars burn blue, white, and violet, producing intense ultraviolet radiation. They live fast and die quickly. Their supernovae send shock waves through surrounding gas, compressing some clouds and dispersing others. The same explosions that can be dangerous to nearby planets also seed the galaxy with oxygen, silicon, iron, and other heavy elements required for rocky worlds and biological chemistry. The solar system's position in the local arm, between larger spiral structures, may be relevant to the long-term stability of Earth's environment. This does not mean Earth is protected by some perfect galactic safe zone. The idea of a galactic habitable zone is debated and difficult to define, but it is reasonable to say that the frequency of nearby supernovae, the density of molecular clouds, and the rate of disruptive stellar encounters are all shaped by a star's galactic neighborhood. Life on a planet is local chemistry, but the background conditions are galactic. The center of the Milky Way is one of the most extraordinary and extreme environments known to science, and it is almost completely hidden from our view at visible wavelengths. The roughly 26,000 light-years of interstellar material between our solar system and the galactic center, gas clouds, dust lanes, dense molecular complexes, absorb visible light almost completely in that direction. The night sky in the direction of Sagittarius, where the galactic center lies, looks to visible light instruments like any other part of the sky, somewhat star-rich, but not obviously different from many other directions. The actual galactic center, with its immense concentration of stars, its active supermassive black hole, and its complex dynamics, is entirely concealed behind that optical screen. Breaking through this obscuration required developing instruments sensitive to forms of radiation less affected by dust than visible light. Infrared radiation, with its longer wavelengths, passes more readily through dust, the same reason sunsets appear red, as dust and air scatter shorter wavelength blue light, but allow longer wavelength red and infrared to pass. Radio waves, with still longer wavelengths, pass through even the densest dust clouds with essentially no absorption. X-rays and gamma rays at shorter wavelengths also penetrate, though their interpretation involves more complex physical processes. The infrared view of the galactic center, provided by space observatories like the Spitzer Space Telescope, the Hubble Space Telescope using its infrared capabilities, and ground-based adaptive optics systems at major observatories, reveals a densely packed region unlike anything in the outer galaxy. Within the central few hundred light-years, a region far smaller than the galaxy as a whole, but still enormous by human or solar system standards, Stars are packed together at densities millions of times greater than the average stellar density in our own neighborhood. The region closest to the galactic center contains young, massive stars that have no business being there according to simple models of star formation. Massive star formation is thought to require the collapse of giant molecular clouds in relatively calm environments. But the environment near the galactic center is anything but calm, with intense tidal forces, strong magnetic fields, and powerful radiation from the central black hole's vicinity that should, by naive reasoning, disrupt molecular clouds before they can collapse into stars. The presence of these young, massive stars in the galactic center region, sometimes called the paradox of youth, suggests that star formation near galactic centers involves physics not yet fully understood. At the very center, within a few light years of Sagittarius A star, is a cluster of stars called the S cluster or S stars, massive, rapidly moving stars with orbital periods ranging from a few years to a few decades, whipping around the central black hole at speeds of thousands of kilometers per second. The S stars are the objects whose precisely tracked orbits provided the key evidence for the mass and position of Sagittarius A star, as discussed in the black holes episode. The most famous of these, S2, has an orbital period of only about 16 years and passes within a few light hours of the black hole at its closest approach, a distance comparable to the diameter of our own solar system, moving at nearly 3% of the speed of light at that closest point. Sagittarius A star is quiet compared with the blazing quasars seen across the universe, but quiet does not mean unimportant. It is the gravitational anchor of the central region. Stars whip around it in tight, fast orbits. Gas clouds are stretched and heated by its tidal field. Magnetic fields thread the plasma around it. The black hole is not currently feeding it anything like the rate it could, but even its low-level activity produces flares in X-ray and infrared light, moments when material close to the horizon heats or rearranges and briefly brightens. The Event Horizon Telescope image of Sagittarius A star did not show the black hole in the ordinary sense. It showed the shadow created by light bending around the region where the event horizon sits. That image matters because it joined two completely different lines of evidence. The long-term stellar orbits proving that a compact mass of 4 million suns sits at the center, and the horizon-scale radio image showing the ring-like emission pattern predicted for plasma moving near a black hole. In a deeper sense, Sagittarius A star makes the Milky Way personal. We do not have to rely only on distant galaxies to study supermassive black holes. One is in our own galaxy, close enough that individual stars around it can be tracked over decades. The center of the Milky Way is not merely a point on a map. It is one of the best laboratories in the universe for testing gravity in the strong field regime. Beyond the very immediate vicinity of Sagittarius A star, the central few hundred light years of the Milky Way contain a complex mixture of features. The central molecular zone, a concentration of dense molecular gas containing a substantial fraction of the galaxy's total molecular gas within a relatively compact volume. The galactic center radio arc, a striking radio feature visible in radio images as a series of parallel filaments apparently oriented perpendicular to the galactic plane, possibly associated with strong magnetic fields channeled along the galaxy's rotation axis, and numerous compact and extended sources of radio, infrared, and X-ray emission reflecting the complex and energetically active environment close to the central black hole. Extending well beyond the central few hundred light years, the galactic bulge, the central thickening of the galaxy that surrounds the bar and gives the Milky Way its characteristic lens-shaped cross-section when viewed edge-on, contains several tens of billions of stars, predominantly older and more metal-rich than the stars in the outer disk. The bulge stars formed earlier in the galaxy's history, in the more metal-poor environment of the early universe, and have since been gradually enriched by generations of stellar evolution, cycling material through star formation, nuclear burning, and supernova explosions that return processed, metal-enriched material to the interstellar medium for incorporation into the next generation of stars. The bar itself, the elongated structure of stars crossing the galaxy's central region, oriented at an angle of roughly 44 degrees to the line connecting us to the galactic center, is a dynamical feature that influences stellar and gas orbits throughout the inner galaxy. Bars and spiral galaxies are understood to be self-sustaining gravitational structures, maintained by the collective gravitational response of the stars within them, an elongated mass distribution that reinforces its own elongation through the orbital dynamics of the stars it contains. Bars are thought to play an important role in the long-term evolution of spiral galaxies, channeling gas from the outer disk inward toward the galactic center along the bar's length, potentially feeding both central star formation and the growth of the central black hole. Our Sun sits roughly 25 to 28,000 light-years from the galactic center, a commonly cited distance often given as 26,000 light-years, reflecting the current best measurements from precision radio astrometry and from modeling the orbits of stars around Sagittarius A star. This places us well outside the galaxy's central concentration, but not at its very outer edge. We sit at about 55 to 60% of the way from the center to the conventional edge of the disk, in the outer regions, but not the outermost. At this distance, the Sun orbits the galactic center with an orbital period of approximately 225 to 250 million years, sometimes called the cosmic year or galactic year. The Sun moves through the galaxy at about 220 kilometers per second relative to the galactic center, considerably faster than you might naively expect for a small star in the outer regions of what might seem like a leisurely rotating disk. In the course of Earth's entire history, 4.5 billion years, the Sun has completed approximately 18 to 20 full orbits around the galactic center. Over those 20 orbits, the solar system has passed through different regions of the galactic disk, different arm environments, different densities of surrounding stars, and has been exposed to different rates of cosmic radiation and varying frequencies of nearby stellar events that may have influenced Earth's geological and biological history in ways that are still actively studied. The Sun's motion through the galaxy is not a perfectly circular orbit. Like most stars in the disk, it oscillates slightly above and below the galactic plane as it orbits, with a period of roughly 30 to 50 million years for each complete up and down oscillation. This oscillation means that over millions of years, the Sun periodically passes closer to the dense midplane of the galaxy, where molecular clouds, star-forming regions, and other potential hazards are most concentrated, and then swings back above or below the plane into the less dense regions. Some researchers have proposed that this oscillatory motion might correlate with periodic increases in the impact rate of comets and asteroids on Earth as the solar system passes through denser galactic regions, though establishing a clear causal link between the galactic environment and Earth's impact history has proven difficult. The solar system's position between the Sagittarius and Perseus arms, in the relatively quiet interarm region of the local arm, is sometimes cited as potentially significant for the development of life on Earth. The interarm region is somewhat less active in terms of star formation and the resulting density of supernovae and other energetic events than the arms themselves. Massive stars, which live short lives and die violently, are preferentially concentrated in and near the spiral arms where they form. An Earth located within a major spiral arm would be more frequently exposed to the ionicing radiation and energetic particles from nearby supernovae, which at sufficiently close range could be genuinely hazardous to biological systems and could potentially damage planetary atmospheres. Whether Earth's relatively benign position in the interarm region is a coincidence or has played some role in enabling the long-term biological evolution of complex life is a fascinating but unresolved question that sits at the intersection of astronomy, geology, and biology. The neighborhood around the Sun also has a history of its own. The solar system sits inside a region called the local bubble, a cavity in the interstellar medium, hundreds of light years across, where the gas is unusually thin and hot compared with the denser clouds around it. This bubble was probably carved by a series of supernova explosions over the past several million years, as massive stars in nearby stellar associations reached the end of their lives and blasted material outward, sweeping the surrounding gas into a shell. This means the Sun is not traveling through a uniform galactic medium. It is passing through a structured environment shaped by the deaths of nearby massive stars. Around the local bubble are denser clouds and star-forming regions, including some of the familiar nearby constellations whose bright stars mark relatively recent star formation. The Sun's current location is not special in a mystical sense, but it is specific, one pocket inside a dynamic, uneven, history-filled interstellar landscape. Some of the iron-60 isotopes found in Earth's geological record may have been delivered by nearby supernovae within the last few million years. These traces, found in deep ocean crusts and sediments, suggest that Earth has been touched by the products of stellar explosions not merely in the ancient formation of the solar system, but in comparatively recent geological time. The galaxy is not only a distant background, it can leave measurable fingerprints in Earth's own rocks. The stars of the Milky Way are not all the same. They span an enormous range of masses, luminosities, sizes, ages, compositions, and evolutionary stages, from dim red dwarfs barely massive enough to sustain nuclear fusion, burning for hundreds of billions of years without ever producing a supernova, to brilliant blue supergiants tens to hundreds of times the Sun's mass, blazing furiously for a few million years before exploding. Understanding the full distribution of stellar types, the initial mass function that describes how many stars of each mass form in any given star-forming event, has been a major achievement of 20th century astrophysics. The Milky Way is also, almost certainly, a galaxy of planets. For most of the 20th century, planets beyond the solar system were plausible but unconfirmed. Now they are known by the thousands. Transit surveys, radial velocity measurements, direct imaging, microlensing events, and timing methods have revealed planets around many kinds of stars. Hot Jupiters close to their suns, compact systems of rocky planets around red dwarfs, super-Earths, and sub-Neptunes unlike anything in our own solar system, cold gas giants in wide orbits, and planets around stars much older or cooler than the Sun. The numbers imply something enormous. If planet formation is common, and the evidence strongly says it is, then the Milky Way likely contains at least as many planets as stars, and perhaps more. Hundreds of billions of stars may mean hundreds of billions of worlds. Most will not resemble Earth. Many will be frozen, scorched, airless, toxic, ocean-covered, or trapped in orbital arrangements unlike the solar system. But the sheer abundance changes the meaning of the galaxy. The Milky Way is not just a sea of stars. It is a sea of planetary systems. This matters because every planet is a potential record of local history. Its composition reflects the chemical state of the disk where it formed. Its orbit reflects the gravitational evolution of its system. Its atmosphere, if it has one, records chemistry, impacts, stellar radiation, volcanic outgassing, escape to space, and perhaps biology. The galaxy produces stars, but around many of those stars it also builds smaller worlds where matter can become complex in slower, cooler ways. Earth is one result of that galactic process, not separate from it, not outside it. but one small outcome of star formation, chemical enrichment, planet formation, and long-term stability inside a spiral disk. The most common stars by far are the smallest, the red dwarf stars, known technically as M dwarfs, that make up roughly 70 to 75% of all stars in the galaxy. These are dim, cool, slow-burning objects, typically between 8% and 50% of the Sun's mass, with surface temperatures between about 2,500 and 4,000 Kelvin, considerably cooler and redder than the Sun's approximately 5,800 Kelvin surface temperature. Despite their dimness individually, their sheer overwhelming numerical dominance means that collectively, they contain a significant fraction of the galaxy's total stellar mass. And because they burn so slowly and so efficiently, they have lifetimes far exceeding the current age of the universe. The oldest, lowest mass red dwarfs will still be burning billions of years from now, long after the Sun has completed its evolution through red giant and white dwarf stages. The Sun itself is relatively typical for the broader population of stars that are not red dwarfs, a G-type main sequence star, what astronomers sometimes call a yellow dwarf, though it's actually more white than yellow and more accurately described as a middle-aged, middle-mass star somewhere around the middle of the main sequence in terms of size and luminosity. It is more massive and more luminous than the majority of stars in the galaxy overall, because the majority are red dwarfs, but unremarkable among the range of Sun-like stars. At the other end of the mass spectrum, the massive blue stars, O and B-type stars, are the rarest but the most visually conspicuous. Their extraordinary luminosity, tens of thousands to millions of times that of the Sun, means they outshine their far more numerous dimmer neighbors so dramatically that they dominate the galaxy's visual appearance in certain wavelengths despite being vastly outnumbered. These stars are concentrated in and near the spiral arms where they form, and their short lives, only a few million years for the most massive, compared to billions of years for the Sun and trillions for red dwarfs, mean their distribution changes on timescales that are short by galactic standards. Following the spatial distribution of O and B stars across the sky is one of the ways astronomers trace the Milky Way's spiral arm pattern, since these stars are still close enough to their birth locations to serve as reliable markers of the regions where current or very recent star formation has occurred. Between these extremes is a rich diversity of stellar types at various stages of their evolutionary journeys. Orange K dwarfs somewhat cooler than the Sun, intermediate mass F stars somewhat hotter, subgiant and giant stars that have evolved beyond the main sequence and are expanding as their hydrogen fuel is exhausted from their cores. White dwarfs representing the cooling embers of stars that have completed their evolution, neutron stars left behind by supernova explosions of moderately massive stars, and black holes marking the endpoints of the most massive stellar lives. The Milky Way contains, in total, something on the order of 100 to 400 billion of these objects in various stages of their life cycles, each one undergoing its own unique sequence of nuclear burning, physical evolution, and eventual endpoint. The interstellar medium, the gas and dust that fills the space between the stars, is not empty in any meaningful sense, and understanding it is essential to understanding how the Milky Way works as a system. The interstellar medium exists in several distinct phases, each characterized by different temperatures, densities, and states of the hydrogen that makes up most of its mass. The cold neutral medium, concentrated in and near the galactic plane, consists of hydrogen atoms at temperatures of around 70 to 100 Kelvin and densities of tens to hundreds of atoms per cubic centimeter, dense enough to be opaque to ultraviolet light from stars. The warm neutral medium, at temperatures of several thousand Kelvin and lower densities, fills a larger volume. The warm ionist medium, heated by ultraviolet radiation from massive young stars and distributed throughout much of the disk's volume, consists of hydrogen that has had its electrons stripped off by photon absorption. The hot ionized medium, at temperatures of millions of Kelvin and very low densities, fills what is sometimes called the coronal phase of the interstellar medium, heated and maintained by the collective effect of supernova explosions that blast hot, energetic gas outward from the sites of stellar death. Within the cold neutral medium are denser structures, molecular clouds, where the gas is cold enough and dense enough that hydrogen atoms have paired up into hydrogen molecules, and where more complex molecules, from carbon monoxide and water to complex organic compounds, form and survive on dust-grained surfaces. These molecular clouds are the nurseries of star formation, the places where the density and cold favor the gravitational collapse of cloud material into new stars. The Milky Way contains thousands of giant molecular clouds, ranging in mass from a few thousand to several million times the mass of our Sun, distributed primarily along the spiral arms where their density is highest. The most famous of these, visible to the naked eye in the southern hemisphere as the dark patches and dust lanes within the Milky Way's glow, are enormous structures spanning hundreds of light years and containing enough material to form entire stellar populations. Interstellar dust, tiny solid particles ranging in size from a few nanometers to a fraction of a millimeter, plays a role in the interstellar medium entirely disproportionate to its mass, which is only about 1% of the interstellar medium's total mass. Dust absorbs and scatters ultraviolet and visible light, reddening and dimming starlight passing through it, and re-radiates the absorbed energy at longer infrared wavelengths. It provides the surfaces on which interstellar molecules form. It plays a role in regulating the temperature of molecular clouds by shielding the interior of dense clouds from the penetrating radiation that would otherwise heat and disperse them. And it carries into the interstellar medium the processed, solid phase products of stellar evolution, the microscopic dust grains produced in the cool outer layers of dying giant stars, expelled into space through stellar winds and supernova explosions, seeding the interstellar medium with the building material for future planetary systems. The interstellar medium also makes the galaxy cyclical. Stars form from gas, live their lives, and return material to space. Low-mass stars shed their outer layers gently in planetary nebulae, enriching the surrounding medium with carbon and nitrogen. Massive stars explode as supernovae, injecting oxygen, silicon, iron, and other heavy elements into the gas around them. Neutron star mergers add some of the heaviest elements, including gold and platinum, through rapid neutron capture processes. Dust grains form in the cool winds of aging stars and in supernova ejecta, then become part of new molecular clouds. A later generation of stars therefore forms from material that has been processed by earlier generations. The Sun itself is not a first-generation star. It formed from gas already enriched by stars that lived and died before it. The iron in Earth's core, the calcium in bones, the oxygen in water, and the carbon in organic molecules are all products of this galactic recycling. This is why the Milky Way is not only a container for stars. It is a chemical engine. Across billions of years, it takes hydrogen and helium left from the Big Bang, processes them through stars, disperses heavier elements, and gathers them again into new stars and planets. The galaxy becomes more chemically complex with time. The possibility of rocky planets, atmospheres, oceans, and life depends on that long accumulation of heavy elements. Beyond the disk itself, the Milky Way is embedded in a vast, roughly spherical halo, a region extending tens to hundreds of thousands of light years above and below the disk plane, containing several distinct and important components. The stellar halo is the sparse population of old, metal-poor stars scattered through the halo volume, representing some of the oldest stars in the galaxy. Some formed more than 13 billion years ago, very shortly after the Big Bang. These stars have highly elliptical or inclined orbits carrying them far from the disk, and their very different chemical compositions compared to disk stars reflect their formation in the early universe, before generations of supernovae had enriched the interstellar medium with the heavier elements that characterize younger stars like our Sun. The stellar halo also contains globular clusters, roughly 150 known clusters in the Milky Way's halo, spherical, gravitationally bound systems of tens of thousands to millions of stars, also predominantly old and metal-poor, thought to be ancient structures dating from the galaxy's earliest epochs. Globular clusters deserve special attention because they are among the oldest visible structures in the Milky Way. A globular cluster can contain hundreds of thousands of stars packed into a roughly spherical system only a few dozen to a few hundred light-years across. In the night sky, through a telescope, such a cluster looks like a glowing ball of starlight, dense at the center and fading toward the edges. But physically, it is an ancient city of stars, old, gravitationally bound, moving through the halo on an orbit that may take it far above and below the disk. Many globular clusters are more than 12 billion years old. They formed when the galaxy was young, before the Milky Way had reached its current structure, before the disk was as chemically enriched as it is now. Their stars are typically metal-poor, meaning they contain lower abundances of heavy elements than younger stars like the Sun. That metal-poor chemistry is not a defect, it is a timestamp. It tells us those stars formed before many generations of supernovae had enriched the galaxy. Some globular clusters may have formed within the early Milky Way itself. Others may be the surviving cores of dwarf galaxies that the Milky Way later captured and stripped apart. This possibility makes them especially valuable. A cluster may look like a simple ball of old stars, but its orbit and chemistry can preserve information about whether it was born here or accreted from elsewhere. In this way, the halo is not empty space around the disk. It is a museum of old structures, globular clusters, ancient stars, stellar streams, and the remains of galaxies that no longer exist as independent systems. The disk is where much of the current star formation happens. The halo is where much of the deep history is preserved. The halo is also home to the remnants of smaller galaxies that the Milky Way has consumed throughout its history. The stellar halo is not a smooth, featureless distribution of old stars. It contains streams of stars, shells of material, and other substructure that reflects the disruption and gradual absorption of smaller satellite galaxies as they fell into the Milky Way's gravitational potential, were torn apart by tidal forces, and had their stars dispersed into long, thin streams along the orbits their parent galaxies once traced. The most prominent of these is the Sagittarius dwarf galaxy stream, a band of stars from a small satellite galaxy currently being digested by the Milky Way, whose orbit has been reconstructed from the spatial and velocity distribution of its disrupted members, showing that it has completed multiple orbits around the Milky Way, shedding stars into a vast, wrapping stream with each close passage. The dark matter halo is the single largest component of the Milky Way by mass, though it is entirely invisible and detectable only through its gravitational effects. Dark matter, the mysterious, non-luminous, non-baryonic material that appears to constitute roughly 85% of all matter in the universe, surrounds the galaxy in a roughly spherical halo extending far beyond the visible disk and stellar halo, gradually declining in density with distance from the galactic center, but still present at distances of several 100,000 light-years. Within the visible disk, The dark matter halo's gravitational contribution significantly augments the gravity of the visible matter, stars, gas, and dust, and is essential for explaining why the galaxy holds together as a coherent structure and why stars in the outer disk orbit the galactic center at the speeds they do. The evidence for the Milky Way's dark matter halo comes primarily from measurements of stellar and gas velocities in the galaxy's outer regions. If the galaxy's mass were entirely accounted for by the visible stars and gas in the disk, simple gravitational physics, the same equations that govern planetary orbits, would predict that stars in the outer disk should orbit progressively more slowly with increasing distance from the galactic center, just as the outer planets of the solar system orbit the sun more slowly than the inner planets. In fact, observations show that stars and gas in the outer Milky Way orbit at roughly constant velocity regardless of their distance from the center, a flat rotation curve that is impossible to explain if only the visible matter is present. The only natural explanation is that the galaxy is embedded in and surrounded by a much larger mass distribution than the visible material alone, the dark matter halo, whose gravity continues to pull on the outer disk even far beyond where any visible material is concentrated. The nature of dark matter, what it is made of, how it was produced, why it interacts with ordinary matter apparently only through gravity and not through any other known force, remains one of the most profound, unresolved questions in all of physics and cosmology. The Milky Way's dark matter halo, like the dark matter halos of all other galaxies, is a major observational phenomenon that demands explanation. But despite decades of increasingly sensitive direct detection experiments, indirect searches through particle physics and astrophysical observations, and enormous theoretical effort, dark matter has never been detected through any means other than its gravitational effects. It is real, its gravitational influence is unmistakable, but what it is remains genuinely unknown. Dark matter also changes how we should imagine the Milky Way's shape. The bright disk is the part human eyes and optical telescopes most naturally notice. But by mass, the disk is not the whole galaxy. The dark matter halo is larger, heavier, and more extended. The stars and gas are embedded inside it. Without that invisible halo, the Milky Way's rotation curve, the fact that stars far from the center keep orbiting at high speeds instead of slowing down as expected from visible matter alone, would not make sense. This is not a small correction. It means that the galaxy we see is only the luminous part of a much larger gravitational structure. The disk is like the visible foam on the surface of a deep, unseen ocean. The foam reveals that something is there, but not the full mass that holds it. Alternative theories of gravity have been proposed to explain flat rotation curves without dark matter, and they remain scientifically interesting in limited contexts. But the broader evidence for dark matter now comes from many independent directions: galaxy rotation, galaxy clusters, gravitational lensing, the cosmic microwave background, and large-scale structure. The Milky Way's rotation curve is one local expression of a much larger cosmological problem. So when we say the Milky Way is our home, we are also saying that our home is built inside a substance we still do not understand. Most of the matter shaping the galaxy has never been directly detected in a laboratory. Its gravity is everywhere in the structure. Its identity remains unknown. The Milky Way's family of satellite galaxies constitutes one of its most interesting and scientifically rich features. The galaxy is surrounded by dozens of smaller galaxies bound to it gravitationally, ranging from substantial dwarf irregular galaxies visible to the naked eye in the southern hemisphere to tiny, ultra-faint dwarf galaxies detectable only through careful surveys of extremely faint, sparse populations of resolved stars. The Large and Small Magellanic Clouds are by far the most prominent of the Milky Way satellites. The Large Magellanic Cloud, at a distance of about 160,000 light-years and containing several billion stars, is the fourth largest galaxy in the local group of galaxies that includes the Milky Way and the Andromeda Galaxy. The Small Magellanic Cloud, at about 200,000 light-years and containing several hundred million stars, is the fifth largest. Both are visible to the naked eye from the southern hemisphere as detached, cloud-like patches of the Milky Way, luminous, irregular structures that, on first encountering them, someone who has grown up in the northern hemisphere and seen only the continuous band of the Milky Way might mistake for clouds or fragments of the main galaxy, separated by some unusual geometry. The Magellanic Clouds are connected to each other and to the Milky Way by the Magellanic Stream, a vast trail of gas stripped from the clouds by tidal interaction with the Milky Way over the billions of years they have been orbiting it. This stream of neutral hydrogen gas stretches for more than 150 degrees across the southern sky, corresponding to a physical structure extending hundreds of thousands of light-years through the Milky Way's halo. The Magellanic Stream is visible in radio surveys of neutral hydrogen emission across the southern hemisphere, and its gas represents material that was once part of the cloud's reservoirs of star-forming gas, stripped away and potentially destined to eventually be accreted by the Milky Way itself, adding to the galaxy's own future star-forming fuel. The Magellanic Clouds may also be more important to the Milky Way than they first appear. For a long time, they were treated as small companions, interesting, visible, nearby, but not massive enough to strongly affect the Milky Way as a whole. More recent work suggests that the Large Magellanic Cloud is massive enough to tug measurably on the Milky Way's halo and disk. It is not merely orbiting passively. It is disturbing the larger galaxy, pulling on the dark matter halo and contributing to the warp and motion of the outer disk. This matters because galaxies are not isolated objects with neat edges. A large satellite can reshape its host. A host can strip gas and stars from its satellites. The boundary between one galaxy and another becomes blurred by tidal streams, shared gas, and gravitational influence. The Milky Way is therefore not just the central disk and bulge. It is a system: disk, bar, halo, satellite galaxies, dark matter, gas streams, and future accretion events. The ultra-faint dwarf galaxies add another layer of mystery. Some contain so few stars that they are barely galaxies in the ordinary visual sense, yet their internal motions imply large amounts of dark matter. They are important not because they are spectacular to look at, but because they test how small a galaxy can be, how star formation begins or fails in tiny dark matter halos, and how well our models of dark matter structure match the real universe. Every satellite is therefore a clue. The bright Magellanic Clouds show active star formation and gas interaction. The Sagittarius Stream shows ongoing destruction. Ultra-faint dwarfs show the dark matter-dominated edge of galaxy formation. Together, they make the Milky Way less like a solitary island and more like the largest member of a small, evolving family. The Large Magellanic Cloud is itself a galaxy in active star formation, containing prominent star-forming complexes including the Tarantula Nebula, also known as 30 Doradus, one of the largest and most intensely star-forming regions known in the local group. A giant H2 region containing young massive star clusters, extended ionized gas structures, and pillars of gas and dust being sculpted by the radiation and stellar winds of the young stars within it. If the Tarantula Nebula were as close to us as the Orion Nebula, one of the best-known star-forming regions in the Milky Way itself, it would cast visible shadows at night from its brilliance. It is a magnificent, overwhelming structure that serves as a reminder of how diverse star formation environments can be and how the conditions within the Large Magellanic Cloud, including its lower overall metallicity, The abundance of heavy elements relative to hydrogen and helium, compared to the Milky Way, create conditions for star formation somewhat different from those typical of our own galaxy. On the opposite end of the scale, the Milky Way's population of ultra-faint dwarf galaxies, discovered primarily through systematic sky surveys over the past 2 decades, particularly using data from the Sloan Digital Sky Survey and more recent instruments, represents one of the most scientifically interesting recent developments in understanding the galaxy's environment. These tiny systems, some containing only a few thousand to a few tens of thousands of stars, have surface brightnesses so low that they were invisible to essentially all earlier observational surveys. They are gravitationally bound systems, not simply chance associations of stars, and their dynamics indicate they contain far more dark matter relative to their visible stellar mass than any larger galaxy, making them the most dark matter-dominated objects known. The theoretical models of galaxy formation based on cold dark matter predict that a galaxy the size of the Milky Way should be surrounded by many hundreds or even thousands of satellite galaxies, far more than the roughly 60 currently known satellite galaxies of various sizes. This discrepancy between prediction and observation has been called the missing satellites problem, and represents one of the most studied challenges for the standard cosmological model. Partial resolution has come from the recognition that many predicted small satellites may have failed to form stars at all. Their dark matter halos exist, but their gas was expelled or prevented from cooling and collapsing into stars by the intense ultraviolet radiation field of the early universe, or by their own small size, making them unable to retain gas heated by supernova explosions. If these hypothetical dark, ghost halos exist in numbers consistent with predictions, the missing satellites problem is alleviated, but dark halos containing no stars are, by definition, essentially impossible to observe directly, and confirming their existence represents an ongoing observational challenge. The Milky Way's future, like its past, is written in the physics of gravity and dynamics, a story unfolding on timescales that dwarf all of human history. For many years, the standard future picture of the Milky Way was described with striking confidence. In roughly 4 to 5 billion years, the Milky Way and the Andromeda Galaxy would collide, pass through each other, and eventually merge into a larger elliptical-like galaxy, sometimes nicknamed Milkomeda. That picture is still physically plausible and remains one of the best-known long-term predictions in astronomy. Andromeda is moving toward the Milky Way along our line of sight. Both galaxies are massive. Their dark matter halos are extended. Gravity will continue shaping the local group over billions of years. But the future of the local group is now understood to be less certain than older simplified descriptions suggested. The reason is that a galactic merger is not determined only by 2 galaxies moving toward each other. The Large Magellanic Cloud matters. The Triangulum Galaxy, also called M33, matters. The masses of the galaxies matter. Their sideways motions matter. Small uncertainties in position and velocity today can grow into very different outcomes over 10 billion years. Recent modeling that includes the gravitational influence of the Large Magellanic Cloud and M33 suggests that a direct Milky Way-Andromeda merger is not guaranteed on the traditional timeline. Some simulations still produce a merger. Others produce a close encounter without a full merger within the next 10 billion years. This does not make the old picture foolish. It makes the future more scientifically honest. The local group is a multi-body gravitational system, and multi-body systems can be sensitive to small uncertainties. The Milky Way and Andromeda are not isolated dancers on an empty stage. They are part of a group with satellites, dark matter halos, and interacting gravitational influences that complicate the outcome. If a merger does happen, it will not resemble 2 solid objects crashing. Stars are so widely separated that direct stellar collisions would be extremely rare. The galaxies would pass through one another gravitationally, their stars deflected onto new orbits, their gas clouds colliding and compressing, perhaps triggering bursts of star formation. Long tidal tails could be drawn out. Spiral structure would be disrupted. Over time, the two systems could relax into a larger, smoother galaxy with a very different appearance from either original spiral. If a full merger is delayed or avoided, the local group's future would still be dynamic. Andromeda and the Milky Way would continue influencing each other. Satellite galaxies would continue falling in. The Large Magellanic Cloud may merge with the Milky Way on a shorter timescale than Andromeda. The Milky Way's disk and halo would continue changing as satellites are accreted and dark matter interactions reshape orbits. Either way, the Milky Way is not permanent in its current form. Spiral arms, bars, satellite streams, star-forming gas, and stellar orbits all evolve. The galaxy we inhabit is a phase in a longer history, assembled from smaller systems in the past and destined to become something else in the future. The Milky Way's past is also a story of growth through merger and accretion. The large, well-formed galaxy we inhabit today was not always this way. It assembled over billions of years through the hierarchical process of smaller structures merging into progressively larger ones, as predicted by the cold dark matter model of structure formation. In the earliest billions of years after the Big Bang, the proto-Milky Way existed as a much smaller, more turbulent, more irregularly shaped collection of star-forming clumps and proto-galactic fragments. As gravity continued to gather material, and as smaller structures fell together, this early system grew, not smoothly and continuously, but through a series of mergers and accretion events, some violent, some gradual. The stellar halo of the galaxy records this history in its structure. The streams, shells, and substructures visible in halo surveys are the remains of ancient mergers, disrupted smaller galaxies whose stars have been partially dispersed into the halo while their more strongly bound cores sometimes persist as distinct globular clusters or ultra-faint dwarf galaxies still visible today. A particularly significant event in the Milky Way's assembly history has been identified through the analysis of stellar velocities and compositions from the Gaia space mission, a European Space Agency observatory launched in 2013 that has been measuring the positions and velocities of more than 1 billion stars in the Milky Way with unprecedented precision, building up the most detailed three-dimensional map of the galaxy ever assembled. Within the Gaia data, astronomers identified a distinct population of stars with chemical compositions and orbital characteristics suggesting they came from a different galaxy, a substantial dwarf galaxy, estimated to have had a mass of several hundred million to a few billion solar masses, that merged with the early Milky Way approximately 8 to 10 billion years ago. This ancient merger event, sometimes called the Gaia Sausage Enceladus event after the research group and publication that identified it, appears to have been a major episode in the Milky Way's formation history, contributing a significant fraction of the interstellar halo's mass and potentially triggering a significant burst of star formation in the early galaxy. The recognition that such a substantial, well-documented merger event occurred within the Milky Way's history has transformed our understanding of how the galaxy grew and evolved over its lifetime, and has opened up an entirely new field of galactic archaeology. Using the detailed properties of stars observed today as fossils preserving information about the long-gone galaxies and events of the Milky Way's ancient past, Gaia has made this history visible in a way older surveys could not. Before Gaia, many ideas about the Milky Way's past were plausible but difficult to test. Astronomers could identify streams and clusters, but the full 6-dimensional information, 3 positions, and 3 velocities, was limited for huge numbers of stars. Gaia changed that. It allowed astronomers to see groups of stars moving together in ways that reveal their origin. The Gaia Sausage Enceladus event is one example. It is not a visible galaxy now. It is a fossil event reconstructed from stars that no longer sit together but still carry related motions and chemical signatures. That is the power of galactic archaeology. The galaxy's past is not written in a book, but in phase space, chemistry, and orbit. Other structures have also emerged from Gaia data. Ripples in the disk, moving groups in the solar neighborhood, streams in the halo, and evidence that the Milky Way has been perturbed by the Large Magellanic Cloud and by past satellite interactions. The galaxy is not in perfect equilibrium. It is still settling. It still carries waves from encounters. It still responds to its satellites. It is alive in the dynamical sense, not biological, not conscious, but continually moving, adjusting, and remembering through motion. This makes the Milky Way less like a static spiral diagram and more like a weather system in gravity. Its stars are collisionless particles compared with gas, but their collective motions create patterns, waves, streams, and scars. The disk is stirred. The halo is built from remnants. The bar rotates. The spiral arms form and fade. The satellite galaxies fall inward. The whole structure is temporary on cosmic timescales, even though it feels eternal from the scale of one human life. There is something quietly remarkable, something worth sitting with, in the full picture of what the Milky Way is. It is more than 100,000 light-years across. It contains more than 100 billion stars. It has been assembling over more than 13 billion years, through mergers and accretion and star formation and stellar death, building up the complex, structured, dynamic system we inhabit today. At its center, 4 million solar masses of matter sit compressed into a region smaller than our solar system, bending spacetime and accelerating stars to a significant fraction of the speed of light in their tight orbits. In its disk, new stars are forming right now. In the molecular clouds of the spiral arms, clouds of gas and dust are slowly collapsing under their own gravity, heating as they compress, eventually reaching the temperature and pressure needed to ignite nuclear fusion and producing stars that will shine for millions or billions of years. Around some of those new stars, planets are forming in circumstellar disks, and on some of those planets, over the immense stretch of cosmic time, the right combination of chemistry and energy and stability might produce something that eventually looks up from its world and wonders where it is. We have done that wondering here, from our ordinary star in an ordinary arm of an ordinary galaxy, and the answers we have found through careful, patient observation and mathematics are far grander than the question first seemed to require. The Milky Way, that pale band of light visible on a clear, dark night, is not a background. It is home. It is the context within which everything that has happened on this planet has taken place. Every breath of air you've ever taken was made of atoms forged in the nuclear furnaces of Milky Way stars that lived and died long before the sun formed. Every element heavier than hydrogen in your body, the carbon, the oxygen, the nitrogen, the iron in your blood, was produced in generations of stars cycling through birth and death within this galaxy, scattered by supernova explosions back into the interstellar medium, gathered again into new stars and planets, and eventually into molecules and cells, and here, in this particular corner of the galaxy, into you. You are not in the universe looking at it from outside. You are made of it, assembled by it, carried through it at 220 kilometers per second on a tiny rock orbiting an ordinary star, 26,000 light-years from the center of a barred spiral galaxy that has been turning slowly for more than 10 billion years and will continue turning for billions more. That is not a small thought, but it is a steady one. The Milky Way is not somewhere far away. It is the structure we are inside, the home that built the materials of Earth, the system that carries the sun, the stars, the gas, the dust, the black hole at the center, the old clusters in the halo, and the future systems still forming in dark molecular clouds. There is one more way to think about the Milky Way, as a system of many clocks. Some of its clocks run quickly. Massive stars form and die within only a few million years, living so fast that their entire existence would occupy only a tiny sliver of the sun's lifetime. Spiral arm cloud complexes form, collapse, are disrupted by radiation and supernovae, and disperse on timescales of tens of millions of years. The hot gas blown out by supernovae expands, cools, mixes, and eventually becomes part of later star-forming material. Other clocks run more slowly. The sun takes more than 200 million years to complete one galactic orbit. The central bar rotates through the disk over enormous spans of time. The spiral pattern changes, but not on human timescales. Satellite galaxies sink gradually inward through dynamical friction, losing energy as they interact gravitationally with the Milky Way's dark matter halo and stars, eventually being stretched into streams and absorbed. Some clocks are almost beyond imagining. Red dwarf stars, the most common stars in the galaxy, will burn for hundreds of billions or even trillions of years, far longer than the current age of the universe. Long after the sun is gone, many of the smallest stars in the Milky Way will still shine faintly. Globular clusters will slowly lose stars. The disk will gradually use up or lose its gas supply. Star formation will decline. The bright, structured spiral galaxy we know now will fade into a different, older state. And yet, for this brief moment in the middle of the galaxy's life, the Milky Way is active and rich. Stars are still forming. Planets are still forming. Satellite galaxies are still falling in. The central black hole still flickers. The Magellanic Clouds still pull on the halo. Gaia is still turning starlight into a map of motion and history. The galaxy is old, but it is not finished. That is the balance that makes the Milky Way so compelling. It is ancient enough to have built generations of stars before the sun existed, but young enough to still be making new systems. It is stable enough to carry the solar system through billions of years, but dynamic enough to preserve the scars of mergers, the waves of satellite encounters, and the slow rearrangement of its disk. Home, at galactic scale, is not a fixed place. It is motion held together by gravity. One final detail makes the Milky Way feel even less like a static object. It is transparent to some kinds of light and opaque to others. Invisible light, dust hides the center. The galaxy appears broken by dark lanes, and the densest regions can disappear completely behind clouds that are cold, dark, and full of future stars. In infrared light, those same dust clouds become more transparent, and the crowded center begins to reveal itself. In radio light, neutral hydrogen draws out the spiral structure across distances impossible to map with visible stars alone. In X-rays, the hot and violent regions appear, stellar remnants, accreting black holes, supernova-heated gas, and energetic activity near the center. In gamma rays, the galaxy becomes a map of cosmic particles and extreme processes. No single wavelength shows the Milky Way as it really is. Each reveals one layer. Visible light shows the nearby stars and the glowing band. Infrared reveals embedded star formation and the obscured center. Radio maps gas. X-rays reveal compact objects and hot plasma. Gamma rays trace the most energetic events. The galaxy is therefore not one image, but many images combined. This is true of our understanding in general. The Milky Way is not known through one discovery. It has been assembled from centuries of observations. Galileo resolving the band into stars, Herschel counting those stars, sharply moving us away from the center. Radio astronomers tracing hydrogen, infrared telescopes seeing through dust, Gaia measuring stellar motions, and modern surveys turning billions of measurements into a moving map. The result is not final. No map of the Milky Way is final. The far side is still difficult. The number and exact shape of the spiral arms are still refined. The mass of the dark matter halo is still debated. The history of past mergers is still being reconstructed. The future with Andromeda is still probabilistic. The Milky Way is known better than ever, and still not completely known. That is what makes it worthy of a long look. Home is familiar, but familiarity is not the same as understanding. The Milky Way in the night sky is also a lesson in scale disguised as something simple. When you see the pale band from a dark place, you are looking along the plane of the galaxy's disk. The band is bright because, in that direction, your line of sight passes through a dense path of stars rather than out of the disk into the thinner halo. The glow is not one object. It is the combined light of millions upon millions of unresolved stars, mixed with dark lanes of dust that block the starlight behind them. This is why the Milky Way looks uneven to the naked eye. In some places, it appears bright and granular. In others, dark gaps seem to cut through it, as if the star field has been torn open. Those dark regions are not empty holes. They are molecular clouds and dust lanes in the foreground, absorbing visible light from the stars beyond them. The Great Rift, visible in dark northern skies as a dark division running through the Milky Way, is one of these dust structures, not an absence of stars, but a curtain of interstellar material between us and the richer star fields behind it. The southern sky reveals some of the brightest and most structured parts of the Milky Way because the line of sight toward the galactic center passes through the constellations Sagittarius and Scorpius. To human eyes, even under excellent conditions, the center is hidden by dust. But the visual richness of that region hints at the density beyond the obscuration. The bulge, the bar, the central molecular zone, the star clusters, and the black hole at the center. From Earth, the Milky Way is therefore both visible and hidden at the same time. We see the glow of the disk, but not the full structure. We see the nearest clouds, but not the far side easily. We see enough to know we are inside something vast, but not enough to understand it without instruments. The naked eye Milky Way is the beginning of the question, not the answer. This is one reason light pollution is not a trivial loss. For most of human history, the Milky Way was part of ordinary human experience. People saw it without needing to travel, without needing telescopes, without needing an app to locate it. It was overhead, night after night, a visible reminder that Earth sits inside a larger structure. Today, for many people living under urban skies, the Milky Way has disappeared completely from everyday experience. The galaxy is still there, but the human relationship to it has been dimmed by our own lights. To see it clearly now often requires distance, from cities, roads, billboards, airports, and the artificial glow reflected by the atmosphere. When the sky becomes dark enough, the band returns. It is not bright in the way the moon is bright. It is soft, subtle, and wide, a structure too large to fit into a single glance. And that softness is deceptive because the quiet band is the visible edge of an entire galaxy. The galaxy also has a magnetic structure, though it is invisible to human eyes. Interstellar space is threaded by magnetic fields, weak by everyday standards, but important across astronomical distances. Charged particles do not move through the galaxy as though through empty geometry alone. Their paths are shaped by magnetic fields. Cosmic rays, high-energy particles accelerated by supernova remnants, pulsars, stellar winds, and other energetic processes, spiral along magnetic field lines, scatter through the interstellar medium, and contribute pressure to the galactic environment. The Milky Way's magnetic field is complex. It follows the spiral structure in broad outline, but is tangled by turbulence, star formation, supernovae, and gas motions. Dust grains align with magnetic fields, polarizing the light that passes through or is emitted by them. By measuring this polarization, astronomers can infer the orientation of magnetic fields across the galaxy. Radio observations of synchrotron radiation, produced by high-energy electrons spiraling around magnetic field lines, reveal another layer of the same invisible structure. Magnetic fields affect star formation because they influence how gas clouds collapse. A molecular cloud is not simply a mass of gas falling inward under gravity. It is turbulent, magnetized, rotating, heated and cooled by radiation, stirred by nearby stars, and sometimes compressed by supernova shocks. Whether part of the cloud collapses into stars depends on the balance of gravity against thermal pressure, turbulence, magnetic support, and feedback from young stars. Star formation is therefore not a simple falling process. It is a negotiation between forces. This makes the galaxy feel less like a static disk and more like a living physical system, not alive in the biological sense, but active, responsive, and full of interacting processes. Gravity gathers gas. Turbulence resists collapse. Magnetic fields guide particles. Radiation heats and ionizes. Supernovae disrupt clouds and create new shocks. Cooling allows gas to settle again. Out of this long cycle, new stars appear. The Sun was born from such a cloud about 4.5 billion years ago. That cloud no longer exists. It has been dispersed, mixed into the galaxy, transformed by time. The Sun's sibling stars, other stars born from the same original cluster, have long since drifted away through the disk. Some may still exist, scattered across thousands of light years, chemically related to the Sun but no longer recognizable as family except through careful measurements of composition and motion. Somewhere in the Milky Way, the Sun's birth siblings are still orbiting, carrying the same ancient chemical signature in their atmospheres. The idea is strangely intimate. The Sun did not form alone. It was born in a cluster or association of young stars, surrounded by radiation, gas, and dust. Over time, gravitational interactions and the general rotation of the galaxy dispersed that birth environment. Earth formed after the Sun, inside the protoplanetary disk that surrounded it, using solid material inherited from the molecular cloud and from earlier stellar generations. The solar system is therefore a local structure formed out of a galactic process. Radial migration adds another layer to this story. Stars in the disk do not always remain at the same distance from the galactic center where they formed. Interactions with spiral arms, the central bar, and giant molecular clouds can change a star's orbit over billions of years, moving it inward or outward through the disk without necessarily making the orbit highly eccentric. This process, called radial migration, means that stars now near the Sun may have formed at different galactic radii, in environments with different chemical histories. The Sun itself may not have formed exactly where it is now. Some models suggest it could have migrated outward from a region somewhat closer to the galactic center, where the metallicity, the abundance of heavy elements, was higher. That would help explain aspects of the Sun's composition compared with nearby stars. The question is not settled, but it illustrates how the galaxy mixes itself over time. Stars are not nailed to their birthplaces. They drift, migrate, and carry their chemical origins into new neighborhoods. This mixing is important for understanding the distribution of planets and the possibility of life. Heavy elements are required to build rocky planets. Early in the galaxy's history, before enough generations of stars had produced those elements, rocky planets may have been less common. Closer to the galactic center, heavy elements are more abundant, but the environment is also more crowded and energetic. Farther out, the environment may be quieter, but heavy elements are less abundant. The actual habitability of a region depends on many factors: metallicity, supernova rate, orbital stability, star formation history, and the details of individual planetary systems. The idea of a galactic habitable zone tries to capture this balance, but it remains uncertain. Life does not happen at the level of a whole galaxy. It happens on planets, through chemistry, energy flows, and long-term environmental stability. Still, the galaxy sets the background. It provides the elements, the radiation environment, the stellar neighborhood, and the frequency of disruptive events. Biology is local, but its ingredients are galactic. The central bar of the Milky Way is another structure that quietly shapes the galaxy. A bar is not merely a visual feature. It changes the motion of gas and stars in the inner disk. Because the bar is an elongated concentration of mass rotating through the central region, it creates resonances, preferred orbital relationships where stars and gas respond strongly to the bar's gravitational pattern. Gas can lose angular momentum through these interactions and flow inward along the bar, feeding central star formation and possibly, over long timescales, delivering material toward the region around Sagittarius A star. This inward flow helps explain why many barred galaxies have enhanced activity in their central regions. The bar acts as a dynamical conveyor, redistributing angular momentum and reshaping orbits. In the Milky Way, the central bar is partly hidden by dust and difficult to map from our location, but infrared observations and stellar motions reveal its presence. It is one more reminder that the galaxy's structure is not decorative. Shape and motion are linked. The central molecular zone, surrounding the galactic center, is one of the most intense gas environments in the Milky Way. It contains dense molecular clouds, strong turbulence, high temperatures compared with ordinary molecular clouds, strong magnetic fields, and complex star formation. Some clouds there appear dense enough that they should be forming stars rapidly, yet their star formation rates are lower than simple models might predict. The environment is too turbulent, too sheared, too dynamically disturbed for the usual rules of calm cloud collapse to apply straightforwardly. This is one of the reasons the galactic center is so scientifically rich. It is not just the location of the central black hole. It is a laboratory for how gas behaves under extreme conditions, how star formation works in strong tidal fields, how magnetic fields and turbulence regulate collapse, and how energy moves between black holes, stars, and interstellar gas. Above and below the galactic center are enormous structures called the Fermi bubbles, vast lobes of gamma-ray emission extending tens of thousands of light-years from the plane of the galaxy. They were discovered in data from the Fermi Gamma-Ray Space Telescope and are thought to record a past episode of energetic activity in the galactic center, perhaps from an outburst of Sagittarius A star or from intense central star formation. Whatever their precise origin, they show that the Milky Way center has not always been as quiet as it appears today. This matters because galaxies have memories written at different scales. A flare near the black hole may last only a short time by galactic standards, but the energy it injects can leave large structures in the surrounding gas. A satellite galaxy passing through the halo can create streams that remain visible for billions of years. A burst of star formation can enrich the interstellar medium and alter the chemistry of later generations. The Milky Way's present appearance is the layered result of many past events, some local, some global, some brief, some ancient. The far side of the Milky Way remains one of the most difficult regions to map. From our position inside the disk, looking across the galaxy means looking through dust, gas, crowded star fields, and overlapping structures. Radio waves help. Infrared helps. Masers and star-forming regions provide precise distances. Gaia helps enormously for stars not too obscured or too distant. but the far side is still less certain than the near side. The spiral pattern there is reconstructed from incomplete tracers, and different models can disagree in detail. This uncertainty is not a weakness of astronomy. It is part of the honesty of the field. The Milky Way is difficult to map because we are inside it, and because the galaxy itself is messy. Spiral arms are not perfect curves. Gas clouds do not sit neatly on diagrams. Star-forming regions are patchy. The bar has thickness and orientation. The disk is warped. The halo contains streams. Satellite galaxies disturb the system. A clean textbook diagram is useful, but the real galaxy is more irregular, more dynamic, and more interesting. New instruments will keep changing the picture. The Vera C. Rubin Observatory will survey the southern sky repeatedly, detecting faint variable stars, moving objects, stellar streams, and transient events. The Nancy Grace Roman Space Telescope will study the crowded central bulge with infrared sensitivity and wide field imaging, making it especially powerful for microlensing surveys and for discovering exoplanets toward the galactic center. The Square Kilometer Array and other radio facilities will improve maps of neutral hydrogen, magnetic fields, pulsars, and the structure of the interstellar medium. Future Gaia data releases will continue refining stellar motions and distances. This means the Milky Way is not a finished subject. It is entering a more precise era. Astronomers are moving from the broad question of what kind of galaxy it is to more detailed questions. Exactly how many spiral arms it has, how the bar rotates, how the disk was perturbed by satellites, how massive the dark matter halo is, how often smaller galaxies have merged into it, how gas flows from the halo into the disk, and how star formation has changed over time. The galaxy we live in is becoming measurable in a way previous generations could not have imagined. But greater measurement does not make it smaller. It makes the complexity clearer. If we could leave the Milky Way and look back from far outside the disk, the view would probably feel both familiar and alien. From above, the galaxy would not look like the bright band we see from Earth. It would look like a flattened spiral system with a luminous central region, a bar crossing the middle, spiral structure winding outward, blue-white star-forming regions tracing parts of the arms, reddish older stars filling the central bulge and bar, and dark lanes of dust cutting through the disk. The sun would not be visible to the eye from that distance. It would be one ordinary point among hundreds of billions, located in the outer disk, far from the dramatic center and far from the bright young clusters of the major arms. From the side, the Milky Way would look thinner and more layered. The bright disk would form a narrow line, with dust lanes crossing it, and a thicker central bulge swelling around the middle. Above and below the disk, the halo would be almost invisible in ordinary light, because its stars are sparse and old. But gravitationally, that halo would dominate the larger system. The visible galaxy would be embedded in something larger than itself. This imagined outside view is useful, but it is also a reminder of limitation. We do not possess such a photograph. Every diagram of the Milky Way seen from above is an artist's reconstruction, built from data, not a direct image. It may be very good science. It may be based on radio surveys, infrared maps, parallax measurements, star-forming regions, and gas velocities. But it is still a reconstruction. We know our galaxy by inference, and the humility of that matters. The Milky Way is also not alone in the broader cosmic web. It is one of the two largest galaxies in the local group, the small collection of galaxies that includes the Milky Way, Andromeda, Triangulum, the Magellanic Clouds, and dozens of dwarf galaxies. The local group itself sits in a larger environment shaped by the Virgo cluster and by still larger structures of filaments, walls, and voids. Galaxies are not scattered randomly through space. They follow the cosmic web, a vast foam-like structure built by gravity from tiny density variations in the early universe. with galaxies forming along filaments and clusters gathering at intersections. The Milky Way is therefore home, but not the whole context. It is a galaxy inside a group, inside a larger supercluster environment, inside the observable universe. The same gravity that holds stars in the Milky Way also shapes galaxy groups and clusters. The same dark matter problem that appears in the Milky Way's rotation curve appears on larger scales in the motion of galaxies and the bending of light. The Milky Way is local, but the physics that explains it is cosmic. One of the most important things the Milky Way teaches us is that ordinary-looking places can be scientifically deep. Our solar neighborhood does not look spectacular. The sun is not at the center. It is not a giant star. It is not near the central black hole. It is not inside one of the most intense star-forming regions. It is not in a famous nebula. It is not even in one of the galaxy's dominant spiral arms. It sits in a relatively calm region of the disk, near many ordinary stars, inside a galaxy that would not look unusual to an astronomer studying galaxies from far away. And yet this ordinary region produced Earth. That is not a contradiction. It may be the point. Long-term biological complexity may require not the most dramatic environment, but a stable one. Enough heavy elements to build rocky planets. Enough time for life to evolve. A star with a long main sequence lifetime. A planetary system not destroyed by close stellar encounters. And a galactic neighborhood where catastrophic nearby supernovae are not too frequent. The conditions that made Earth possible may depend less on being special and more on being allowed to remain stable for a very long time. The Milky Way also gives time a different shape. Human history is short. Recorded history is a few thousand years. Agriculture is about 10,000 years old. Homo sapiens is a few 100,000 years old. Complex life is hundreds of millions of years old. Earth is 4.5 billion years old. The Milky Way is older still. Many of its globular clusters formed when the universe itself was young, before the sun existed, before Earth existed, before the elements that would become Earth had been gathered into a solar nebula. When we say the galaxy has turned for more than 10 billion years, the phrase is almost too large to mean anything emotionally. But you can make it slightly more concrete. The sun has completed only around 20 orbits since Earth formed. One galactic year is longer than the time between the first dinosaurs and today. The entire history of human civilization occupies an invisible fraction of the sun's present orbit around the galactic center. This does not make human life insignificant in any simple way. It changes the scale of the stage. The galaxy is not aware of us, but we are aware of it. The atoms in our bodies were made by it, and somehow, in one small part of it, matter became capable of reconstructing the larger structure that produced it. That is not a sentimental claim. It is a physical one. The galaxy made the elements. The elements made planets. One planet produced observers. Those observers learned to map the galaxy. The Milky Way therefore becomes a loop of understanding. We are inside it, made by it, unable to step outside it, and yet capable of building a model of it from measurements gathered within it. That is one of the quiet achievements of science, not escaping our perspective, but correcting for it. There are still enormous unknowns. We do not know the exact mass of the Milky Way. Estimates differ because much of the mass is dark matter, extending far beyond the visible disk, and because measuring the motions of distant halo tracers is difficult. We do not know the precise shape of the dark matter halo, whether it is spherical, flattened, elongated, or changing with radius. We do not know exactly how many ultra-faint satellites remain undiscovered, hidden by distance, low brightness, or the limits of current surveys. We do not know whether every predicted dark matter subhalo contains stars, or whether many are completely dark. We do not know every detail of the spiral structure. The Milky Way may have two dominant arms with additional spurs, or a more complex pattern depending on which tracer is used. Gas, young stars, old stars, dust, and masers do not always draw exactly the same map. The galaxy may not have one simple spiral pattern at all, but overlapping structures with different lifetimes and pattern speeds. We do not know the complete history of Sagittarius A star. Today it is quiet, but the Fermi bubbles and other evidence suggest that the central region has been more active in the past. How often did the central black hole flare? How much did it influence the surrounding gas? Did past activity affect star formation in the central molecular zone? These questions connect the Milky Way to the broader study of how black holes and galaxies regulate one another. We do not know how common Earth-like outcomes are inside the galaxy. We know planets are common, but common planets are not the same as common life. We do not know how often rocky planets have long-term stable climates, protective magnetic fields, active geology, oceans, atmospheres, and the right chemical history. We do not know whether life is rare or widespread, simple or complex, silent or detectable. The Milky Way may be full of living worlds, or Earth may be an unusual result of many unlikely conditions. The galaxy does not answer that question easily. What it does give us is scale. Hundreds of billions of stars, billions of years, heavy elements built and recycled, planets forming across the disk, ancient clusters in the halo, dark matter holding the structure, a central black hole bending space-time, satellite galaxies falling in, stars being born while others die. The Milky Way is a system large enough to make human life seem tiny, and rich enough to make that tiny life part of an enormous physical continuity. That continuity is the strongest thread through the whole subject. The galaxy is not separate from Earth. Earth is one expression of the galaxy. The air, the oceans, the rocks, the iron core, the carbon chemistry of life, the calcium in bones, the silicon in continents, and the uranium that helps heat the planet's interior all come from the long chemical evolution of the Milky Way before the Sun formed. We are not only located in the galaxy, we are materially descended from it. So when we look at the Milky Way, we are not looking at something foreign. We are looking at the larger system that produced the local world we call home. The Milky Way is also a story of measurement becoming more precise over time. At first, the galaxy was a visual impression, a band in the sky. Then it became a field of stars through Galileo's telescope. Then it became a flattened system through Herschel's star counts. Then Shapley moved the sun away from the center using globular clusters. Then radio astronomy revealed hydrogen gas across the disk, allowing astronomers to trace spiral structure through dust that visible light could not cross. Then infrared astronomy opened the hidden central regions. Then astrometry from space began to measure stellar distances and motions at a scale that earlier astronomers could only imagine. Each step changed the picture. The Milky Way went from cloud to star field to disk to barred spiral to dark matter-dominated system to evolving archaeological record. The galaxy itself did not change during those centuries. Our ability to read it changed. This is a useful reminder because the Milky Way can feel familiar. Its name is old. Its appearance is ancient. It has been overhead since before language. But scientific familiarity is different from visual familiarity. We have only recently begun to understand the galaxy as a dynamic system with a merger history, a warped disk, a central bar, a dark matter halo, streams of accreted stars, and satellite galaxies that actively disturb it. The next century will almost certainly change the map again. More precise Gaia releases will refine the motions of stars. Infrared surveys will clarify the bulge and far side of the disk. Radio surveys will trace the cold gas more completely. Gravitational wave astronomy may detect compact object populations that help map stellar remnants in the galaxy. Microlensing surveys may reveal planets that are too distant or too faint for other methods. The Milky Way is not only a subject we study, It is a nearby laboratory for almost every major branch of astrophysics. Consider how many different kinds of objects the galaxy contains. There are cold brown dwarfs, too small to sustain ordinary hydrogen fusion. There are white dwarfs slowly cooling for billions of years. There are neutron stars with magnetic fields trillions of times stronger than Earth's. There are pulsars flashing with clock-like regularity. There are black holes, most of them invisible unless they accrete matter or disturb a companion star. There are planetary nebulae, supernova remnants, open clusters, globular clusters, molecular clouds, Ionis nebulae, stellar nurseries, runaway stars, hypervelocity stars, and rogue planets drifting between stars without a parent sun. A galaxy is not one kind of thing. It is a population of many kinds of things held in one gravitational structure. The Milky Way contains the full life cycle of stars: birth in cold clouds, long main sequence burning, expansion into giants, death into white dwarfs or neutron stars or black holes, and the return of material to the interstellar medium. It contains the birthplaces of planets and the remnants of destroyed systems. It contains both the raw material for future stars and the ancient fossil record of stars formed near the beginning of cosmic history. It also contains silence. Between the stars are enormous distances. Even in the disk, where the density is high compared with the halo, stars are separated by light years. The galaxy is rich, but it is mostly empty by volume. A spacecraft traveling at human technology's current speeds would need tens of thousands of years to reach the nearest stars, and millions or billions of years to cross meaningful fractions of the galaxy. The Milky Way is home, but it is not small. It is local in the cosmic sense and unreachable in the human sense. This contrast is part of what makes it powerful for a sleep documentary. The galaxy is familiar enough to be personal and vast enough to quiet the mind. It contains our world and exceeds every ordinary scale. It is close because we are inside it, and distant because even its nearest stars are impossibly far by human standards. There is no need to make the Milky Way dramatic artificially. It already is dramatic, but quietly. It does not need explosions in every paragraph. Its calmest facts are already enormous. The sun moving around the center, the galaxy turning slowly, the dark matter halo holding the disk, the atoms of Earth forged in older stars, the future of the local group still uncertain, the map still incomplete, the home galaxy still being discovered from within. That is the emotional center of the subject. The Milky Way is not merely a place where astronomy happens. It is the place from which we do astronomy. It is both the object and the vantage point. We study it while belonging to it. There is also a moral of scale hidden in the Milky Way, though not a moral in the human storytelling sense. The galaxy does not arrange itself around us. It does not know where Earth is. It did not form with human observers in mind. The sun is not central, not unusually massive, not unusually bright, and not located in a privileged region. For a long time, astronomy has repeatedly moved humanity away from imagined centers. Earth from the center of the solar system, the sun from the center of the galaxy, the Milky Way from the center of the universe. Each displacement could seem like a diminishment, but the deeper view is more interesting than simple diminishment. We are not central, but we are connected. We are not outside the galaxy looking in. We are a temporary, local structure made from its material. The fact that the Milky Way is indifferent does not make it irrelevant. Its history is physically written into us. Every breath depends on oxygen produced by stars. Every cell depends on carbon made in stellar interiors. Every red blood cell depends on iron that came from ancient stellar death. The rocks beneath us are not merely planetary. They are galactic material that passed through generations of stars before becoming part of Earth. The Milky Way is therefore not a backdrop to life. It is part of the chain of causes that made life possible here. This perspective also changes the way the night sky feels. The Milky Way is not only something above us. Above is a local direction. The galaxy surrounds us in all directions, including below the horizon, including the region hidden by daylight, including the far side blocked by the Earth itself. When you stand on Earth, you are not underneath the galaxy. You are inside it, rotating with a planet, orbiting with a star, circling with a disk, and moving with a galaxy through the local group. Nothing about ordinary experience is built to notice that motion. The ground feels still. The stars seem fixed. The Milky Way looks like a quiet band. But stillness is only local. On larger scales, everything is moving. Earth spins, Earth orbits, the Sun orbits, the galaxy rotates, satellite galaxies fall inward, and the local group moves through the expanding universe. That is the kind of calm this subject offers. Not the calm of smallness, but the calm of belonging to a system larger than any single worry, any single day, any single human timescale. The galaxy is vast enough that personal urgency becomes smaller, and real enough that the thought is not fantasy. It is astronomy. One last scientific point belongs near the end. The Milky Way is not only a place of matter, but a place of memory. A galaxy remembers through structure. It remembers a merger as a stream of stars. It remembers star formation as clusters and chemical enrichment. It remembers supernovae as expanding remnants, hot bubbles, and heavy elements mixed into later generations. It remembers the pull of satellite galaxies as warps, ripples, and disturbed stellar motions. It remembers the early universe in the metal-poor stars of the halo and the ancient globular clusters still orbiting far from the disk. This memory is not conscious, of course. It is physical. Gravity preserves orbital patterns. Chemistry preserves birth conditions. Light preserves distance and time. Motion preserves disturbance. When astronomers read the Milky Way, they are reading these physical traces and reconstructing events that no human being could ever have witnessed. That is why the galaxy can feel quiet and still while being historically rich. Nothing needs to happen quickly for the story to be powerful. The Milky Way's most important changes unfold over millions and billions of years. A satellite galaxy can take multiple orbits to dissolve. A spiral arm can reshape star formation over immense timescales. A red dwarf can outlive the current age of the universe many times over. A globular cluster can carry stars from the early universe into the present. The night sky compresses all of that into a band of pale light. It looks simple because our eyes are limited. The science opens it back up. And even now, while the galaxy turns, the map is changing. New stars are being born inside clouds that no human eye can see directly. Old stars are losing their outer layers back into space. Dust grains are forming, breaking, charging, and drifting. Cosmic rays are crossing magnetic fields. Gas is cooling in some places and being heated violently in others. Satellite galaxies are losing stars to the halo. The central black hole is quiet, but not dead. The local arm continues carrying the sun through its long orbit, and Earth continues turning under a sky that only seems still because our lives are short. The Milky Way is not finished, and neither is our understanding of it. Every better survey, every cleaner parallax, every new infrared map, every radio measurement of gas, every stellar spectrum adds another small correction to the picture. The galaxy becomes clearer slowly, the same way it formed slowly, by accumulation. Perhaps that is the most honest final image of the Milky Way, not a completed diagram, but a home still being measured. A child can see its glow from a dark field. A telescope can resolve its stars. A radio dish can trace its hydrogen. An infrared observatory can look through its dust. A space mission can measure its stellar motions. A theoretical model can follow its mergers backward and its future forward. None of these views is complete alone, but together they turn the familiar band of light into a galaxy, structured, moving, ancient, and real. And because we are inside it, every clearer measurement is also a clearer measurement of our own location. The Milky Way is not only the object being studied, it is the coordinate system of our existence. That makes the galaxy both scientific and intimate, measured by instruments, but lived from within every second, and still being discovered. And we leave it there, not as a pale band in the sky, but as a living galaxy in motion, ancient, vast, unfinished, and still carrying us around its center. Good night.